Welcome to the second lecture in our course Analysis of a Complex Kind. Today we'll be talking about algebra and geometry in the complex plane. We'll learn what the complex numbers are, how to add them, how to multiply them, how to subtract and divide them, and some of their properties. Complex numbers are simply expressions of the form z equals x plus I y, where x and y are simply real numbers. For example, z equals 3 plus I times 5 would be a complex number. Often that is just written as 3 plus 5i. So it doesn't really matter if the I comes before or after. X, this first number right here, is called the real part because there's no I attached to it, whereas y, the second number with the I in front of it, is called the imaginary part, or in short, x is re of z, the real part of z, and y is im of z, the imaginary part of z. The set of all complex numbers is denoted by a c for a complex plane. This is like a c with a double bar in it, so regular c with an extra bar in it. That's the mathematical symbol for the complex plane. The real numbers are considered a subset of the complex numbers, those for which that second parameter, that y, is simply equal to 0. So a number of the form z equals x plus 0i is considered a real number. And so the real numbers are kind of subsets of the complex numbers. So our regular numbers 3, 6, 7, they're all included in the complex numbers. The complex plane can be identified with R2, and here's how that goes. We often draw an actual plane, so like a coordinate system, and we use the x-axis for the x-coordinate, which is the real part of z, and we use the y-axis for the imaginary part of z. And with that convention, we can then draw a complex number, z, which is of the form x plus iy, where the coordinates are here x, the x-coordinate, the real part of z, and the y-coordinate is the imaginary part of z. And thereby the real numbers are actually sitting on that x-axis. And numbers on the y-axis are called purely imaginary numbers. Now, how do we add complex numbers? Suppose we have a number z, which is of the form x plus iy, and we have a second number w of the form u plus iv. How do we add them? So here we're defining the addition of complex numbers. We're defining them by simply adding the two numbers that don't have any i's attached to them, so the x and the u. We add those two numbers, so those two real numbers. And then we add the y and the v and put the I in front. And so our new complex number, our resulting complex number, has a real part, which is the sum of the two real parts, and has an imaginary part, which is the sum of the two imaginary parts. In other words, the real part of z plus w is simply the real part of z plus the real part of w, and the imaginary part of z plus w is simply the imaginary part of z plus the imaginary part of w. Let me give you an example. Suppose we're adding the numbers 3 plus 5i plus, let's say, minus 1 plus 2i. The way to do that would be simply to add the 3 and the negative 1. 3 plus negative 1 equals 2. And then add the 5 and the 2, and that's a 7i. Graphically, the addition of two complex numbers could be represented as a vector addition. So let's go back to our coordinate system. Suppose we have a vector z right here. I'll draw it as a vector, even though it's really a point in the complex plane. And suppose we have a second vector w, which would be right here. So that's u plus iv. If we wanted to add these two vectors, all we would have to do is we move the beginning of z to the end of w and sort of complete this parallelogram that you can see right here. And the vector in the middle, the diagonal vector, that corresponds to the vector z plus w. So this point right here is z plus w, and what we've done there, we have indeed added the x of z and the u of w. So from here to here, that distance is exactly the same as from here to here, which corresponds to the length u, and on the other hand, the same is true on the y-axis. So addition of complex numbers corresponds to a vector addition. The modulus of a complex number is the distance of that number from the origin, or the length of the vector from the origin to the point z. So again, if I draw my complex plane and suppose I have a point z equals x plus iy, then this is the x coordinate, and here's the y coordinate. And suppose I'm asking how far is z from the origin. So I'm asking for this length right there. How long is that? And I'm going to call that the modulus of z, that length. Well, I can see there's a right triangle right here. And in order to find the length of the hypotenuse in that right triangle, all I need to do is I square the lengths of the two legs. But how long are those legs? This leg right here has length x squared. Well, that's the square of this leg. This leg has length y, so y squared. And together, that gives me the length of the hypotenuse squared. So z squared is x squared plus y squared, or in other words, z itself is the square root of x squared plus y squared. Now, how do we multiply complex numbers? Here's the motivation. Let's pretend for a second that they behave just like normal numbers that we know from elementary school. So suppose I have a number x plus iy, and I wanted to multiply that with u plus iv. And suppose all the regular rules held, so I can just distribute this out the way I'm used to. Then I would get x times u by multiplying this number with this number, plus ixv from here, and then I get iyu, and then I squared yv. So I would get exactly these four terms. Now, if I indeed has the property that I squared is -1, then this should really just be a -1 here. Now, this is a motivation. So this is the thought that goes into this following definition. If this is supposed to be true, then the part of this number that is real will consist of this xu, because there's no I in there, and this number right here, because I squared is -1, so minus yv is also a real number. So the real part of the product of these two complex numbers should then be xu minus yv. And the imaginary part would be this together with this, so xv plus yu. And indeed, that's how we define our multiplication. So let's look at an example. Suppose we wanted to multiply 3 plus 4i by -1 plus 7i. So what I have to do according to this formula, I have to take the x and multiply it with the u. That gives me a -3. Then I have to take the y, which is the 4, multiply it by v, and put a negative sign in front of the product. So 4 times 7 is 28, minus 28. Then I'm going to get the complex part by taking x and multiplying it with v. So 3 times 7, that's this 21. And finally, I take y times u. So this is y, and u is here. So 4 times -1 is -4. Then I simplify. -3 minus 28 is -31, and 21 minus 4 is 17. So the result of this product is again a complex number, and it is -31 plus 17i. Now one can check that with this definition, the usual properties of multiplication still hold, even though we're now multiplying complex numbers and not just real numbers. And those are, for example, that z1 times z2 times z3. If you want to multiply three numbers, it doesn't matter if you multiply the first and the second first, and then take the result and multiply it by the third, or you multiply the second and the third, and then the first one times that result. This is called associativity. You can move these parentheses around and decide which multiplication gets executed first. Multiplication is also commutative, which means it doesn't matter if I write this factor first and then this factor, or if I write this the other way around. So in fact, this would be the same thing as -1 plus 7i times 3 plus 4i. You should check this out. Get out a piece of paper and apply this formula to this product and verify that indeed you do get the same result, -31 plus 17i. Finally, our multiplication is distributive. So if I have three complex numbers and I have to multiply z1 by the sum of z2 and z3, I could also multiply this out and multiply z1 and z2 and multiply z1 and z3 and add them up. That's called the distributive law. So all these laws still hold. Now what exactly is I, that number I? So far it's kind of just a symbol that's been sitting there. Well, I is certainly the same as 0 plus 1 times I. And so I can now calculate I squared, because I is 0 plus 1 times I, and the other I is also 0 plus 1 times I, and I can use the rule of multiplication that I just defined to find out what this is. So according to my rule of multiplication, I have to take this 0 and that 0 and multiply them, and that gives me this number right here. Then I have to take this one and that one, multiply them and put a negative sign in front of it. That's what I get right here. Then I have to take this 0 and that one and multiply them. And finally, I have to take this one and that 0 and multiply them, and these two form the imaginary part together. So 0 minus 1 is -1, and all the rest is 0. So I squared is indeed -1. So the multiplication we defined has the property that we wanted it to have. I squared equals -1. So what is I cubed? Well, I cubed is I squared times I. By the associativity, we just realized it doesn't matter which one I multiply first. I squared is -1, so I cubed is -1 times I, so it's -I. I to the fourth, well, I could write that as I squared times I squared. Each of these I squareds, as we just showed, is -1, so that's -1 times -1 and -1. What's I to the fifth? Well, that's I to the fourth times I. I to the fourth, we just showed, is 1. So it's 1 times I, which is just I. I to the sixth, well, that is I to the fifth times I. I to the fifth was I squared is -1, and it keeps going. So what have we noticed? I is I squared is -1, I cubed is -I, I to the fourth is 1, and then these four numbers keep repeating. So I squared is -1, I cubed is I to the fourth is 1, I to the fifth is I to the sixth is -1, I to the seventh is I to the eighth is 1, and it keeps repeating like that. So there's really just four different states that a power of I can have. So how do you divide complex numbers? Suppose we're given a z, x plus iy, and a w, u plus iv, so two complex numbers. How do I divide z by w? And of course I'm going to need w to be non-zero. I can't divide by 0. So here's a great trick, and I'll show that to you with actual numbers. So z over w would be x plus iy over u plus iv. Let's do this whole calculation with actual numbers. So suppose z is 3 plus 4i, and so suppose w is -1 plus 7i. And I wanted to calculate this quotient. So I wanted to calculate 3 plus 4i and divide that by negative 1 plus 7i. How do I do that? Well, the idea is to multiply top and bottom by this number u minus iv. So almost the same as the bottom, but I'm multiplying it by the bottom number with a plus replaced by a minus. So in our example here, I would have still my top 3 plus 4i divided by negative 1 plus 7i. But now I would multiply top and bottom by negative 1 minus 7i. So it's almost the same as the bottom, but I'm replacing this plus here with a negative sign. Now, when I multiply this out, on top, I have a regular multiplication of two complex numbers. So I'm going to get here 3 times negative 1 is negative 3. Then 4 times negative 7 is negative 28, but I'm going to have to make it a plus because that's how the multiplication goes. And then plus I times, and I need to multiply the 3 by the negative 7, so that's negative 21. And the 4 by the negative 1, so minus 4. And what happens in the denominator? I have a u squared plus v squared, so I'm just going to multiply this through here. Negative 1 times negative 1 is 1. And I have a 7 times a negative 7, that's negative 49, but I'm going to make that a plus, so plus 49. And then I get plus I times negative 1 times negative 7, that is 7. And 7 times negative 1 is negative 7. And now, let's see what happened. So on top, I have in this example here 28 minus 3, so that's 25. Plus I times, and here I have minus 21 minus 4 is minus 25. In my denominator, I have a 50, and the imaginary part went away. And so in other words, this simplifies now to a complex number. I have no more i's in the denominator. And so I can simplify this. 25 divided by 50 is simply 1/2 plus I times, and here I have a minus 1/2. I could have pulled the minus sign out and put it right here, but this looks exactly like our complex numbers look. In other words, when I divide complex numbers, the result is again a complex number. And the trick we used was to make the denominator real. And how do we do that? We make the denominator real by multiplying the denominator u plus iv by u minus iv. We also multiplied the numerator by that so that we would have equality. So we just multiplied top and bottom by u minus iv. But the trick was that that made the imaginary part cancel out. And so the denominator became purely real, so that we could then separate real and imaginary part of the result. So here's the result. Here's a formula for the quotient of two complex numbers. In particular, if we just wanted to calculate 1 over z, so not z over w, but just 1 over a complex number, it's 1 over x plus iy, and again we would do the same thing. We would multiply top and bottom by x minus iy, and if we do that in the bottom, the imaginary parts would cancel out and we would just end up with x squared plus y squared, as long as, of course, z is not 0. So 0 plus 0i would be bad. We couldn't be dividing by that. But this is 1 over z. So this quantity x minus iy, where we just replaced the plus with a minus, that was really important in the previous calculation. And it's so important that we give it a special name. So if z equals x plus iy is a complex number, then we call that complex number where we replace the plus with a minus the complex conjugate of z. And it's denoted with a z with a bar on top of it. You see that here? So z bar is the complex conjugate of z. So let's look at some of its properties. If you conjugate twice, you end up with the original number. So if you take the conjugate here, which is x minus iy, and you take another conjugate of that, All you do is you flip the sign in front of the imaginary part. You're going to end up with x minus iy. And minus is plus, so that's x plus iy. And we're back to the original number we started with. So taking the conjugate twice gets you back to where you started. What does taking the conjugate mean graphically? Let's go back to our coordinate system. And let's suppose I have a complex number z right here, which is x plus iy. Then where is the complex number x minus iy? Well, here's x, and there's y. Well, now I'm going to retain the x for the complex conjugate, but I'm making the y negative. I'm taking minus y instead of y. And so in other words, I'm going to get this number right there for the complex conjugate, x minus iy. So the complex conjugate is the number z, but it's reflected with respect to the x-axis. Now here's a property of complex numbers. If I take the complex conjugate of a sum of two complex numbers, I might just as well take the conjugate of z first, and then the conjugate of w, and then add those two numbers up. That's a property one easily verifies. The absolute value of the conjugate is the same as the absolute value of z. Well, you can kind of see that in my picture right here. This length right there is the length of z, and down here is the length of the conjugate of z. And because this is just a reflection of that, these of course have the same length. A little hard to see in my picture, but because it's just a reflection, they have the same length. Now here's a really neat property. Z times its conjugate, that's what we were making use of in our calculation of the quotient. This is x plus iy times x minus iy. And when I multiply through, I get x times x, which is x squared. I get y times minus y, which is minus y squared, but together with a negative sign that I get from the I squared, so plus y squared. And I get x times minus iy, and x times plus iy, that cancels out. So I get x squared plus y squared, which is the length of z squared. So z times its conjugate is actually the length of z squared. And that means we can rewrite the formula for 1 over z. 1 over z now becomes, I multiply top and bottom by z conjugate, so z times z conjugate, and then the numerator of z conjugate, and the denominator simplifies to length of z squared. So 1 over z is the conjugate of z divided by the length of z squared. Now, when is it the case that the conjugate of a number is equal to the number itself? We learned that the conjugate is simply a reflection with respect to the x-axis. So when is the reflection with respect to the x-axis the same as the number itself? So when is this number equal to its own reflection? Only if the number was on the real axis to begin with. So this is the case if z is a real number. Now here's another interesting thing to note. If you add a number and its complex conjugate, what you end up doing is x plus iy plus x minus iy. So you add the x and the x, you get 2x. And then you add the complex parts, the iy and the minus iy, they cancel each other out. So you get something real. In other words, if I divide this equation by 2, I get the x, which is the real part of z, is equal to z plus its conjugate over 2. So we find a nice formula for finding the real part of a complex number. We add the number to its conjugate. And similarly, if you take a complex number and subtract the conjugate, then you get 2i times the imaginary part. So if you want the imaginary part by itself without the I, you're going to have to divide by 2i. So this is also a nice formula. Now you can verify that the length of z times w is the length of z times length of w. So length and multiplication behave well with respect to each other. You can also verify that the conjugate of z over w is the conjugate of z over the conjugate of w. And finally, that the length of z is 0 if and only if z was 0. Now this is pretty easily verified because the length of z, remember, let's look at the square of the length. That's just x squared plus y squared. And x squared plus y squared, when is that equal to 0? These are two real numbers. When can that be 0? They both have to be 0. So this is 0 if and only if x is equal to 0 and y is equal to 0. And that means if and only if the number z itself was the number 0. Now we have some inequalities that are really helpful. One of them is pretty obvious by looking at a picture. Let me draw the complex plane right here. And there's a complex number z right there. Then this is the real part of z. This length right there is the real part of z. Whereas this length right here is the norm or the length of z. And this length right there is the imaginary part of z. So this is the real part of z and that's the imaginary part of z. And since they form a triangle, I see that this length here is certainly greater than or equal to either one of those two legs. And that's what's expressed here. The real part of z is less than or equal to the absolute value of z, and the same is true for the imaginary part. And because that's true in absolute value, we get the other inequality easily as well. An inequality that's also very nice is the triangle inequality. The length of z plus w is bounded above by the length of z plus the length of w. Let me show you in a picture why that is the case. So let's add two complex numbers, z and w. So remember how we do that? We do a vector addition. So here's z. And suppose we wanted to add to that w. Then what we have to do, we have to complete this parallelogram. And this is our point z plus w. And it can be represented by this diagonal. This is the length of z plus w. And if I look over here, this length here, that was the length of z. And here I see the length of w, because it's the same vector as this one down there. And again, these form a triangle. My triangle didn't really meet very nicely over here. These three lengths form a triangle, and the shortest path from the origin to z plus w is certainly this diagonal, and a slightly longer path is to go along z first and then along w. So z plus w is greater than or equal to the direct path z plus w. That's what the triangle inequality says. There's a reverse triangle inequality that follows from the triangle inequality. It's z minus w is greater than or equal to z minus w. Won't go into much detail there. Finally, a little outlook into the future. This is the fundamental theorem of algebra. You may have heard of it. Suppose we have complex numbers a0, a1 through an, and this an, this last one, is a non-zero number. And you look at this polynomial. So, for example, again, if you'd like to have an example in mind, you could look up the polynomial p of z equals 5z cubed plus 4z squared minus 2z plus 14. So in this case, 3 would be the largest n that we have here, so a3 would be 5, a2 is 4, a1 is negative 2, and a0 is 14. So this is called the degree 3 polynomial, and this theorem says that such a polynomial has n roots, so in this case has 3 roots in c, so 3 z's for which p of z can be equal to 0. And it can be factored as an times z minus the first root, z minus the second root, and so forth. We'll be able to prove this theorem later on in this course. Now, in R, this was totally not true. This is a special fact about complex numbers. For example, look at the polynomial p of x equals x squared plus 1. So we have a degree 2 polynomial, but we're only considering it for real numbers and not for complex numbers. This never ever crosses the x-axis. So if I graph this polynomial, x squared plus 1 is always above the x-axis. It never crosses the x-axis, so it's never equal to 0. And so we can't factor it either. It has no real roots. But if you looked at that as a polynomial in C, so z squared plus 1 instead of x squared plus 1, and we're allowed to not only plug in real numbers for the x, but also complex numbers, then I can find two complex numbers, namely I and negative I, for which this term right here is actually equal to 0. I squared plus 1 is 0, and minus I squared plus 1 is also 0. And so it actually factors. So this is a theorem about complex numbers, and we will be able to prove this later on using complex analysis in this course.